Okay. Are there any questions before we get started? Okay, no questions. Let's get started. So we are talking about linear time invariant systems. We have been talking about frequency response, which we call H omega. Okay, and this is also called a transfer function in many systems. And H omega is nothing but the ratio of the output to the input. Maybe something like VO out and V in out. Okay, just the ratio of the output to the input. The output and the input can occur in different forms. Okay? And these are ratios in what we call the frequency domain, because they're in the phasor world. Okay? And this is a linear time invariant system. H of omega describes the transfer function of the frequency response of this linear time invariant system. So if you have f1 of t coming out is y1 of t, then if you have the same system, dipole, okay, you have f2 of t, and coming out is y2 of t. Okay, since we have a linear time invariant system and a dipole system here, okay, so if you have k1 f1 of t plus k2 f2 of t, what should be the output for this system? Very good. Okay, output would be k1 y1 t plus k2 y2 t. Okay. For sinusoidal system, we make this extremely simple. We say if it's a sinusoidal system, I'm going to use the word sinusoid. So of course sinusoid. I think it's simple. Okay. For sinusoidal system, f1t might be something of this form. The real part of f1 e to the j omega t. Okay, f2t might be something of the real part of f2 e to the j omega t. And f1 and f2 are phasors, or phasor forms of f1t and f2t. Okay? And if those are the inputs, and you will get sinusoidal signals as output. Okay? y1t would be sinusoidal and will be something times e to the j omega t. So if f1t is written in that form, if the frequency response or the transfer function is of that form, what do you think y1t is? And what should you insert there to make things come out correct? Yes?
K into F1?
What?
K into F1?
No.
Oh, why?
If F1 is coming in this way, and if F1 is something of this form, then I'm asking for what Y1 should be. And you should be able to insert the blank, fill in the blank. Okay? You seem to be very happy. What is the answer? What?
H times F1.
Which F1?
The phasor.
Okay. H of omega times F1. Very good. And what happens if I try to be a little bit different? If I say these two signals are of different frequencies. Okay, if they are of different frequencies. Does this third rule still hold true? Would this still hold true?
No.
Who said no? You say no? Alexander, you're wrong. Okay? It should be still true because it's still a linear time invariant system. Okay? So even if they are of different frequencies, if this one comes in as a sinusoidal frequency 1, this one comes as a sinusoidal frequency 2, this principle still holds true. Okay? So if I'm going back to this step, and frequency is important. Frequency is important. So what would be the frequency of y1t if you have a sinusoidal input at frequency omega 1? What would be the frequency of this output, you think? Yes? True thing? Still omega 1, right? Still omega 1. And then what should I be careful about this h omega? Can I use any value from the frequency response, or I have to be careful about picking a frequency?
Omega 1.
Omega 1, very good. So this should be omega 1. Similarly, y2 of t would be the real of the transfer function as the selected frequency, which I will ask you to give me later on. Okay, e to the j omega 2t. What is the frequency I should pick here to make things come out correct? Omega 2, very good. Okay? Then if I have a linear superposition of these two signals, okay, what is the output? Let me call this aggregate output maybe O. Maybe not a very good name. O is not a very good name. Let me call it G of t. Okay? How about I write G of t? If I know that these are the two outputs for example 1 and example 2, G of t would be real of, how would I fill in the blank here?
H omega 1 and 1 plus H omega 2 alternate
Did you say that?
e to the j omega 1t.
E to the j omega 1t, that's very important. Okay? Times the k1. There's a k1 here. Okay, let me put the k1 properly. k1h of omega 1. And then the second term should be k2 h of omega 2 times f2 e to the something. What is that e to the something that I should put up here? J omega 2t. This is a characteristic of a linear time invariant system, and that thing still holds true. Okay, so that is the aggregate output. And notice that these two are at different frequencies. Okay? So is this clear? So if this is clear, then you can change the number of inputs. You can change the number of inputs from 2 to 3 to 4 to any numbers that you can work with. Okay? And the principle of linear superposition still holds true. So let me write something in the book. And then the book would say that if this is my input, since the real part is only important when you want to convert this into a real signal, this thing is actually going around in a circle. So if this has been my input, okay, and then if it goes through the linear time invariant system with h of omega, what would be the output? The output previously, before taking the real part, was this one. Okay? Then I can say that the output should be h of omega 1 f1 times e to the j omega 1t. Okay? So you see a lot of pictures like this in the textbook, where there's no real part operator involved. because this is obvious, right? Because taking the real part is only necessary to convert this into real signal. It's also necessary to convert this into real signal. But since this is going round and round in a circle, if the real part is equal to each other, the complex signal coming in must also give the same output. Okay, you will see a lot of things like this in the textbook. Okay, and then you might want to say that f1 is equal to 1, and then you'll put something like f1 equals to 1 in the textbook. Okay, so when you see a picture like that, don't get confused. So let's do example 5.6 on the textbook, where we have a transfer function or a frequency response which is given by this. Okay? And then we have two signals, two sinusoidal signals. One is 2 sine of 0.5 t. Okay? The other signal is f2 of t is equal to cosine of 2t plus pi over 4. Okay? What is the output signal when I have the sum of these two signals? Okay? You can actually do that or do them individually. I can say that this is the same as the real part of 2 e to the j 0.5 t. Actually, I did this example, right? Did I not? Or maybe not. I did this example. I did not do this example in the last lecture. E to the j 2t plus j pi over 4. Okay? Then, what is y1t? y1t would be the real part of this value, which is the input multiplied by the transfer function. The transfer function is given by this. Okay, and then multiplied by e to the j omega t. And what should I evaluate my omega at? If the input is at this frequency, I should use the transfer function's value at 0.5. Okay, so this should be evaluated at 0.5. And omega should be evaluated at 0.5. Okay, then you get the right output. And you can work out the detail. The rest is just phasor techniques, right? It's 0.5, so you get j over 1 plus 0.5j e to the j 0.5t. And then do some vector complex algebra and convert that into Cartesian form and then get the output. Okay, y2t would be equal to the real part of, if you look at a phasor that has been here, what is the phasor representation of f2 of t? If you look at this equation over here. Alexander. You're Alexander, right?
Oh, me?
Yeah.
Yeah.
Okay. What is the phasor representation?
Sorry, I can't see here.
Oh, okay. Here.
The phasor representation.
Phasor representation of this thing.
Don't know.
Don't know? Okay, let's rewrite this. Let's rewrite this up here. So write this as real part of e to the j pi over 4 e to the j omega t. Omega t here is just 2t. And then say that this thing being equal to that thing over there. So what is the phasor representation of that? George? E to the j pi over 4, right? E to the j pi over 4, very good. Okay, that is the phasor representation of this signal. And then the next thing you should do is to multiply by the transfer function. the transfer function should be evaluated at what frequency now? 2, right? So it should be J2 over 1 plus J2. This is where the transfer function should be evaluated. And then it should be multiplied by the same frequency and taking the real part of this. And you can work out all the complicated, complex number algebra. Okay? I wouldn't work that out for you unless you want me to work them out for you. I presume you know how to do that. Okay? And then you can get a signal for this one. And then what happens if you have a input that is F3 T is equal to K1 F1 plus K2 F2? You just use the principle of linear superposition and work this out. I won't go through the detail and work this out for you. Okay? Are there any questions so far? Yes, Alexander.
I think your real portion, version for f1 of t is incorrect because it's 2 sine of 0.5 t, so shouldn't it be 2j?
Oh yeah, you're very good. Okay, should be 2j. Okay, should be 2j. You're right. 2 minus j, I think. Right, that's very good. You caught me on that. So there should be 2 minus j here. Okay, let me think. Yeah, it should be 2 minus j. Okay, that's very good, Alexander. Okay, so you work that out and that should be great. Any other questions? Okay, let's see. We have looked at different kinds of transfer functions or frequency response. The first one we looked at was this one over here. Okay, and the second one we looked at was this one over here. And then the third one that we looked at was this one over here. J omega over 1 minus omega squared plus j omega. Okay? And if you write this in terms of magnitude and phase, then the first one is actually equal to 1 over 1 plus omega squared e to the minus j up tangent of omega. Okay, so that's what you get for the first one. The second one, you will get omega magnitude plus 1 plus omega squared magnitude square root of, that gives you the magnitude of the numerator and the denominator. Then the phase will look something like this. But you have to add the phase of the numerator. The phase of the numerator is just the plus or minus j pi over 2. Depending on whether, if you take the phase of this numerator, it is 90 degrees when omega is positive, and then it is minus 90 degrees when omega is negative. And the mathematical way of writing that actually is to take this to be the sine function, omega. So that should be correct. Okay, so the phase of that is equal to that. And then the third one, the magnitude of the numerator is just that, and then the magnitude of the denominator is equal to that square plus omega squared square root of. Okay? This is called a sine function. This is called a sine function. And it has this property that sine of omega, it has the sign of plus 1 when omega is positive, and then it has the value of minus 1 when omega is negative. So you put that right there, the sign would come out correct. Yes?
In the denominators of the first two functions, shouldn't it be the square root of 1 minus omega squared, since you have a j squared, and that's a negative 1?
No, no. Okay, if you have a complex number, real, and then imaginary, and then you have a complex number that's 1 plus j omega. Say the imaginary part is j omega, the real part is just 1. In order to find the magnitude of this complex number, you find the length of this line. Okay, the length of that line is equal to 1, and this height here is omega. Okay, you use Pythagoras Theorem. This is 1 plus omega squared, taking square root of. So this one will be square root of 1 plus omega squared. Okay? Then if you let this go minus omega squared, then we will be catastrophic, because there will be certain values of omega where the length becomes 0. Right? If I define the length with the minus sign here, then the length can shrink to 0, even though omega is not 0. And it will be catastrophic. Okay, it's defined in such a way that the length can never be 0. Okay? And let's do the third one. The third one is more difficult. So it will be e to the minus j arctangent of omega over 1 minus omega squared. That is the sign coming from the first part. And then the numerator will give you a contribution that is plus j pi over 2, the sine function, just like before. Okay? And then there's always this concept of half-power bandwidth. The first function, you remember what it was called? The first function was called the first function came from a certain circuit. It was called a kind of a filter. Very good. It's called a low-pass filter. The second one is called a high-pass filter. The third one is called a band-pass filter. Very good. Okay, if you remember, if we plot the magnitude of the first one, it looks something like this. H of omega looks something like that. That's a function of omega. If you plot the second one, if you recall that, it looks something like this. Okay, this has value of 1, I believe. This is value of 1. The third one, if you recall when we plotted it, it has something that looks like that. Okay, this is called a bandpass filter. And I think we all understood the physics of it. The first one comes from a circuit that looks like one. If you have a voltage source, and it is a low-pass filter, which means that only low frequencies can go out of the output. So it must be something like that. So this is V in, V out. So that at low frequency, the capacitor looks like an open circuit, so you get a huge voltage drop from VI, but at high frequency, the capacitor looks like a short circuit, and it has a very low output. Okay, the second one looks more like this. And at low frequency, the capacitor acts like an open circuit, okay? And V out is 0 because no current can flow. Okay, and then high frequency currents can flow through the capacitor, and that is okay. Okay, this one looks something like this. I think you can have a current source or a voltage source here. Doesn't matter. This one is more complicated. Okay? And if you look at V out over V in, it will look something like that. And then there's this concept of half power bandwidth. Okay, what is the concept of half power bandwidth? or half power frequency. Let me just define the frequency where the power becomes half of its peak. This thing is a ratio of voltages. Okay? This thing is a ratio of voltages. But power is proportional to voltages in what way? Power is proportional to the square of the voltages. Okay? So if you want something that represents power, you will have to square the transfer function. Okay? Because if you think about this, that H of omega is, say, VI over V, VI over VI, right? But then if you want something that represents power, then you should take the square of this. This will be something like V naught square over VI square. And this represents ratio of power, because power is proportional to V naught square. So if I were to square that plot, it will look pretty much the same, but maybe narrower. H square would look something like this for the first plot. Okay. The half power frequency is where this thing drops to half. You find the omega naught and omega naught where the power drops to half of its peak. That is called a half power frequency. Okay? This is called the half power frequency. This is minus omega naught. Okay? And then there's the concept of decibel. If you were to define the transfer function in terms of decibel, then you actually have to do something like this. H of omega in decibel, or decibel is written as dB. Okay, dB stands for decibel. Or maybe just lowercase. I don't know if this is written as uppercase. Decibel. Okay, decibel is defined to be 10 log base 10 of h of omega squared. Okay, so if you were to express this quantity in decibel, you will have to take the log square of that function and multiply by 10. Because 1 decibel is 1/10 of a bell. To measure things in decibel, you multiply by 10 to make it 10 times larger, because 1 decibel is 1/10 of a bell. And 1 bell is the log of the square of the function, or the ratio. Okay? So this is something that you should know. And why do people like to do this? People like to do this because if you were to express things in terms of decibel, and say if you were to plot this function in terms of decibel, the low values will get stretched and amplified. Because log of 0 is minus infinity, right? So you will stretch this diagram. If I just plot the right half, if I just plot the first one in terms of decibel, okay, which means I take the log of that square, it will not look like that anymore. It will look to be slowly dropping and then dropping rapidly to negative value. Okay, because those very small values will become negative. And you stretch out this curve so that you can see these negative values very, very well. Okay, that's why you want to plot things in decibel. Okay. So, there are certain numbers that you should remember in terms of decibel. that if you have half, the value of half from the peak, like the half power, in terms of decibel, what is this number? You take the square of that number and multiply, or take the square of that number, take its log and multiply by 10. So this would be something like log 10 base 10 of half square. Okay? So this would be like 20 log of 2 with a negative sign, right? Because it's log of half. You have log of half first. Log of half is minus log of 2. What is log base 10 of 2? Log base 10 of 2 is about 0.3010. Okay? So I remember that. Okay.
He committed that to memory.
Wow.
And then, so that turns out to be about minus 3 dB. Okay? So when somebody tells you a minus 3 dB, it becomes a electrical engineering speak. A lot of you will have to speak like that. Okay, what is 3 dB? Minus 3 dB, half power bandwidth, half power frequency. Okay, 3 dB means half the power. Not exactly, it's 3.010. Okay, but you can ignore the 010. It becomes electrical engineering speak. Okay, yes?
What's the units for decibels?
It has no unit. It's a ratio. Remember that this is a ratio between two things. You're taking the log of a ratio, so it has no unit. You can think of this as a bell, a tenth of a bell, then so it becomes decibel. Okay, it's a measure of ratios. Okay, so this 3 dB means the ratio of something. Okay, and then you should remember that if you have 1, what does 1 map to in terms of decibel? What? No? If you take log of 0, log of 1, it becomes 0. 0, right?
Yeah.
You get, if you plug into this formula, it's 10 log of 1 squared, which is 0. So 0 dB means 1. Okay, nothing happens. And then you have 2. Okay, it becomes plus 3 dB. It's just the opposite of this one. If you plug 2 in, you get plus 3 dB. And then 4, if you get a signal 4 times larger, okay, it becomes 6 dB. And then if you get something that's 10 times larger, you get 10 dB. And then you get something that's 100 times larger, it's 20 dB. Okay, those are electrical engineering speak. Okay, you will have to learn how to speak in this language when you go out to work. Your boss will most likely talk to you in this language, not this language. Okay? And if you buy anything from the shop, they might also speak in this language. Okay?
If it's 10, should it be 20 dB?
What is that?
If it's 10.
10 is 10 dB according to
because
what I have.
10 log 100, right? 10 log 100 is 20.
No, these are actually, I have in my note here to be 10. Okay? Let me see.
Oh, it's 20.
10 log 100 is 20.
Right.
And 100 should be 40 dB.
Let me see, I took this out of the book. Let me see if the book says something.
I thought this was the language of like
You're right, this is the language of electrical engineering. So what I have here is that this should be actually, these are power. These are actually power. Okay, so if this is power, then I should have no square here. Okay, I shouldn't put a square there because I already squared this number. Okay, so if I put that there, then it should be 10. And then log of 2 should be something like 3 dB. So I got something wrong somewhere. 2 is, log of 2 is equal to
Log 2 is 0.3.
0.3010, right? So I get 3 dB, that's right. This converts to 3 dB, okay? So 2 converts to 3 dB, these are power. Okay, and then 4 converts to 6 dB. And then 10 converts to 10 dB, 100 converts to 20 dB. So when you're talking about power, these are the correct ratio. But if you talk about voltages, you have to take the square root of this. If this is voltage, okay, this would be 1 over root 2, this would be 1, this is root 2, this is 2, this is root 10, this is 10. Okay, if you think in terms of voltages, this would be the ratio in terms of voltages. This would be the ratio in terms of power. And then this would be the numbers in terms of dB. Okay? Okay. Let's see how much time I have left. I have some time left. Let's go to section 5.4. Do you have any question on this?
How many of them do you remember?
What is that?
How many of them do you remember?
I don't remember a lot of them. Because I don't work in the lab a lot. If you work in the laboratory a lot, better remember these numbers.
No, I think an easy way to remember is log 2 is 0.3, log 3 is 0.4, log 4 is 0.5. It comes out to be approximately.
Right, right. So I think the thing you have to remember is log of 2 is 0.3010. If you remember this, you remember a lot of things. Okay? And then you can figure out the other numbers. Okay, let's do section 5.4. And I think this is kind of mundane. I think I more or less taught you this.